Mathematics is divided by deep chasms. Number theory speaks in discrete algebraic structures. Analysis speaks in continuous, complex functions. Bridging them is one of the most significant challenges in modern number theory. The Birch and Swinnerton Dyer conjecture, or BSD, rests on this divide. It seeks a precise equality between two distinct fields of mathematics. The algebraic side is the rank of rational points on an elliptic curve. It measures the number of independent, infinite directions generated by the curve's group law. The analytic side is derived from the L function. We calculate its order of vanishing at the central point, s equals 1, to determine the analytic rank. For these two numbers to be compared through geometry or spectral theory, they must exist in the same mathematical space. We need a shared arena where discrete algebra and continuous analysis can be measured by the same ruler. Establishing that connection requires a coordinate system that respects both languages. Without a shared rigorous geometry, the algebraic and analytic terms remain isolated. This image shows the real points of several elliptic curves. Could these Cartesian plots serve as our shared space? No, these curves are bounded, consisting of isolated circular components. Their independent loops are capped at 2. Topologically, the real curve is restricted. Many elliptic curves have an algebraic rank of 3, 8, or higher. The physical real curve has no mechanism to generate the additional loops necessary to represent these higher ranks. Because the topology of the real curve is limited to a Betti number of 2, it cannot act as a general map for high-rank arithmetic. This forces us to move beyond the physical plot. Another possibility is to map the infinite orbit of the rational points themselves to see if they trace a continuous shape. However, a countable set of distinct points will not form a continuous closed loop. No matter how many points are calculated, they remain discrete markers in space. To create a shared space, we cannot rely on the physical representation of the curve. Instead, we must synthesize a geometry directly from the algebraic group of points. This requires building a multidimensional topological space derived from the free Mordell-Weil group. This chart outlines the pipeline to translate pure algebra into a continuous manifold. First, removing the torsion subgroup identifies the free Mordell-Weil lattice. Next, tensoring with real numbers expands it into a continuous space. Finally, quotienting by the original lattice yields the Mordell-Weil height torus. This construction provides a bridge. It converts a discrete algebraic group into a measurable, continuous geometric object. The height torus functions as a dictionary that maps arithmetic properties onto geometric ones. The torus's independent loops perfectly equal the algebraic rank. A rank 3 curve yields a torus with 3 independent directions. Here, a rational point becomes a closed geodesic path. The squared physical length of this geodesic exactly equals the point's canonical height. On the height torus, algebraic rank is recorded as topological dimension, and canonical height is recorded as physical distance. This dictionary also extends to the metric properties of the curve, specifically the regulator. These two plots represent different height tori. Both have a rank of 2, sharing the same loop topology, but their metrics differ, clearly visible in the area of their blue fundamental parallelograms. This squared Riemannian volume exactly equals the elliptic curve's regulator. This powerful translation allows the complex algebraic regulator to be explicitly calculated through the differential geometry of the height torus. We can now apply this geometric toolkit back to the original BSD conjecture. Hodge theory tells us that the zero modes of the Laplacian operator on a manifold correspond to its independent loops. This permits a reformulation of the conjecture. We replace the algebraic rank with the dimension of the Hodge-Laplacian's kernel on the height torus. This doesn't prove the BSD conjecture, but it provides an exact geometric reformulation of the target. By identifying this target geometry, we clarify the structural landing pad that the analytic side of the equation must connect to. It is tempting to assume that the zeros of the L function are simply the eigenvalues of this new torus. This log-log plot demonstrates a counting law obstruction. L function zeros grow at t log t, while a flat torus spectrum grows at t to the power of r. Because these are structurally incompatible, no linear rescaling can ever force the spectra to match. A valid bridge requires building two independent pipelines, one for the analytic explicit formula and one for the topological Hodge trace. The comparison must be based on their residual, calculated without using the expected rank as an input. The BSD bridge remains uncrossed. However, by establishing this rigorous geometric target, we have a fixed point for future analytic comparisons to aim for.